Hello everyone, my name is Rachel and I'm here to present a paper titled Using Explainability Tools to Inform NILM Algorithm Performance, a Decision Tree Approach. Since load disaggregation via NILM was initially proposed, NILM researchers have been focusing on improving disaggregation performance. However, the trustworthiness of NILM model itself has hardly been addressed. Therefore, the focus of this paper is on explainability of DT as a multi-classifier, taking input from the smart meter and to explain the output. To explain multi-classifier output, we use explainability tools as follows: partial dependence plots, individual conditional expectation plots, and feature importance. Why decision tree? It's a low complexity supervised approach, requires small dataset to train, has shown good performance and can be used as multi-classifier. It is also interpretable by nature such that it can be followed through from the parent to the leaf node to understand how the outcome came to be. However, at times, the tree can become too complex and the dependence of predicted outcome on a feature is not easily seen. Therefore, it is important to use other explainability tools to shed light on most important features that the model uses for a particular outcome. As previously mentioned, the explainability tools used in this paper are feature importance, ICE, and PD plots. The figure seen here is the feature importance graph. Feature importance provides global explanation. It is calculated as number of samples of the features that reaches the leaf node divided by the total samples of the feature. So it gives the score to each input feature based on how useful it is for the prediction of the outcome. In this figure, it is observed that feature named edge n is considered by the model among all the input features the most important with a score of about 0.035, and edge p the least important feature with a score of 0. The figure seen here displays both ICE and PD plots. Y-axis is the score from 0 to 1 of the predicted outcome with respect to features. Both PD and IC plots visually show the relationship between input feature and the predicted outcome and assume the features are not correlated with each other. The difference between them is that PD plot, presented by the red line, provide global explanation. Therefore, it does not show feature distribution like ICE plots. For instance, in this figure, it is observed that PD plot is flat and has low score of 0.2. This indicates, on average, edge n feature is not considered important for prediction keto. ICE plot, on the other hand, provide local explanation, as we can actually see how individual instances of a feature are distributed and which are considered important and which aren't. These individual instances of a feature are represented by the black dots. We observe from this figure that there are some instances of edge n features focused on the region between negative 3700 watts and negative 2000 watts at the score of 1 of y-axis. These show a very high impact on the prediction keto. The instances, that is the black dots, at the score of 0 show no importance on the prediction keto. The black lines you see in this figure simply show the distribution of edge n feature instances. So it is seen from the figure that while PD plot value is low on average, but there are few instances that have very high impact on prediction keto. To generate features, we use edge detection algorithm to isolate edges by comparing delta P with adaptive threshold. P is the aggregate power measurement at sampling instant T. The figure on this slide represents some of the falling and rising edges for microwave and toaster occurring simultaneously. The first rising edge is the toaster rising edge, followed by microwave rising edge. Microwave falling edge is between 160 to 180 seconds. The second green line from the right. So basically, the edge detection algorithm will try to identify the corresponding rising and falling edges by comparing these edges with the adaptive threshold. The event detection algorithm will output the following features. Edge P, that is the positive edge when the appliance becomes on in watts. Edge N, that is the negative edge when appliance becomes off in watts. Duration, time elapsed between positive edge and negative edge in seconds. All other delta P that do not belong to the appliance of interest are labeled as other, representing unknown appliances. The features are used as input features and appliances are the output. After training the model, it is then exported to predict the unseen data without labels. For DT multi-classifier, data used are of house 2 of refit for training and testing. The appliances used are washing machine, dishwasher, microwave, toaster, and kettle. These appliances are chosen because they are common in most houses, are appliances with similar power signature, such as washing machine and dishwasher, thus cause the most misclassification. These appliances include a mix of single on-off state, such as kettle, and multi-state appliances, such as washing machine. For benchmarking purposes, we used house 2 data. Training is done on 55 edge pairs per appliance, taken randomly from house 2 data, excluding the testing months. Testing is done on entire months of October, November, and December of 2014. Adaptive thresholds used are as follows: 2000 watts for kettle, 1900 watts for dishwasher and washing machine, 1000 watts for microwave, and 700 watts for toaster. For performance evaluation, the following standard classification metrics are used: precision, recall, and F-score. These are the results of the 5 classifier. We observe kettle having the best performance and washing machine having the least performance. To understand this outcome from the model, we first plot the feature importance graph. It is observed that the model, in general, considers edge N and duration to be more important than edge P. Edge P is the least important feature as per feature importance graph. However, the model considered edge P important for prediction keto as seen by the rise of the PD plot in the figure below. Due to keto's high and distinct power signature, edge P instances, highlighted in green, at the score of 1 are very well clustered and do not mix with other instances. PD plot is also observed to rise for about 60% with these values. This is why keto obtained its high performance as the unseen data has HP values above 2700 watts. The only issue we see here is that one HP value at about 2400 watts at one score highlighted in purple that is seen to be mixing up with instances at 0 score between 2000 watts and 2600 watts highlighted in purple, where kettle is likely to be confused as either a washing machine or dishwasher. This single instance caused kettle PD plot to rise for only about 60%. Age n and duration have a lot of mixed up instances, as highlighted in purple, to be of any significance for prediction kettle. Although we see a rise in duration PD plot, indicating there are some duration instances at score of 1 that may not be mixed up with instances at score 0, and of importance to kettle, it is still difficult to distinguish kettle from microwave and toaster as they have similar duration. From the figures here, we observe HP being somehow important for microwave as well, even though there are a lot of mixed up instances around the same wattage highlighted in purple. We see few that are at score of 1 and not mixed up with any other instances highlighted in green. With HN instances lesser than negative 1180 watts are considered strongly for prediction microwave, highlighted in green. Microwave performance is affected as seen in the performance table because the unseen data has instances that are larger than negative 1180 watts, where microwave is easily confused by toaster, seen in the next slide, as they have similar power signature. Duration is not important for microwave as seen by mixed up instances around the same time. Age n values greater than negative 1160 watts in green are considered strongly for prediction toaster. However, as in case of microwave, toaster performance is affected as seen in the performance table because the unseen data used for testing have values that are lesser than negative 1180 watts, hence false negatives. HP and duration show low confidence in prediction toaster as there are a lot of mixed up instances around the same wattage and seconds respectively. Washing machine and dishwasher have similar power signature as well, and hence easily confused with each other. Observed in the ICE plots with HP, a lot of mixed up instances highlighted in purple. With HN, the model leans toward washing machine with values between 2281 watts and negative 2216 watts and about negative 1937 watts. We see the PD plots rising with these instances as highlighted in green. Nonetheless, the rise is not too much, indicating low confidence in the prediction. With duration feature, instances between 270 seconds and 540 seconds and higher than 780 seconds have higher impact on prediction washing machine, as highlighted by green. The PD plots with this instance rise for about 60%. Hence, duration is more important for prediction washing machine. As previously mentioned, washing machine and dishwasher have similar power signatures well, and hence easily confused with each other, observed in the ICE plots. With HP, a lot of mixed up instances highlighted in purple. With HN, the model leans towards dishwasher with values between negative 2280 watts and negative 2567 watts, and about negative 2,215 watts and negative 2,038 watts. We see the PD plots rising with these instances highlighted in green. Nonetheless, the rise is not too much, as in washing machine, indicating low confidence in prediction. With duration feature, however, instances between 270 seconds and 280 have high impact on prediction dishwasher. The PD plot with these instances can be seen to rise about 60%. Hence, as in washing machine, duration is more important for prediction dishwasher. To summarize, although the model in general considers HP as the least important feature, in prediction, microwave and kettle, HP is important. Microwave and toaster confuse easily with each other. They can easily be separated with HN as a feature, as seen by how HN instances in their IC plot have been clustered well. Duration is not an important feature for microwave, toaster, and kettle, as they have similar operating duration, but very important for prediction, dishwasher, and washing machine. In this section, we try to improve the model by training the features the model deems important. The table on the upper right corner shows the result of the model that is trained with only the two important features. First, we train the model with HN and duration. Then we train the model with HN alone. Improved performance has been highlighted in bold. The table in the upper left corner are the results of the classifier when trained with both three features. As previously discussed, we first start with HN plus duration. HP is important for kettle and microwave. Hence, removing HP has dropped performance of these two appliances, as seen by more false negative in the figure labeled B in the right side. Secondly, toaster is not affected by the removal of HP. We saw previously that the prediction toaster needs HN feature. And third, washing machine and dishwasher have improved performance as HP was bringing more confusion as seen in the table on the upper right corner. When the model is trained with HN only, first, with HN only, we saw a lot of mixed up instances in kettle. Even the PD plot was flat and low, so HN only will only bring more false negatives in kettle, as seen in the figure labeled C in the bottom right corner. Toaster, microwave, and kettle prediction require both HN and HP. Since they are appliances with similar duration, duration as a feature will bring more confusion with these appliances. Therefore, HN only has not improved performance of these three appliances. With HN only, washing machine and dishwasher performance has dropped since it was previously discussed that dishwasher and washing machine requires duration as a feature. To conclude, we have seen how explainability of a model provides better understanding of how the feature relates to the prediction overall and on each instance. Thus, in turn, can be used to improve the model performance. Although in general, the model considers specific features important, individual instances are essential to explain false positives. Further work is required to improve the performance of challenging appliances such as dishwasher and washing machine, as well as transfer learning with DT. Thank you.